Okay, so we are back again. So although it's a dynamics course, but we have to see little bit of steady state analysis, right? So computation of steady state values. So for stability analysis, it is necessary to find the initial steady state values of machine variables as a function of specified terminal quantities, right? So it is assumed that all the quantities are expressed in per unit. So whatever analysis we will do, we will make it in per unit, right? It's a normally terminal active power Pt, reactive power Qt and magnitude of voltage Et are specified. Therefore, the corresponding terminal current IT and power factor angle phi are computed as follows. So, I2 will be root over Pt square plus Q2 square upon Et. I mean suppose if you have a this, suppose you have a bus bar, right, and suppose here you have the power say Pt plus jQt say, right, and voltage here say Et, right, say Et tilde the phasor quantity, and your what you call the current is say it is your IT, right. So, when you write your load flow studies you have studied. So, when you write the power equation, that is your Pt power injection equation, Pt minus jQ8, we can write that Et tilde conjugate IT, right. So, these are all Et and IT, they are phasor quantity. So, if you take the your what you call that your IT, what is that value of IT, then I can write that IT is equal to Pt minus jQt divided by Et tilde conjugate, right. So, I mean if you take the magnitude of this IT, then we can write say if IT is the magnitude of the current, right, then we can write IT is equal to root over Pt square plus Qt square divided by Et, that is what it has been written here, right. So, that means your that is your IT, and similarly your power factor, that cos phi will be Pt upon Et IT. Et is the magnitude, IT is the current. So, if Pt is the real power and Et IT is the volt ampere, therefore, cos phi will be Pt upon Et IT, therefore, phi is equal to cos inverse Pt upon Et IT, right. Now, this B part. The next step is to compute the internal rotor angle delta I. Since Eq tilde lies along the q axis, this we have seen earlier, as given in figure below, the internal angle is given by, I mean this is that phasor diagram, that Eq, this is my q axis, say I have drawn like this is my q axis, right. So, this is Eq tilde is equal to your Et tilde plus RAIT tilde plus JXQ tilde, this we have seen, right. So, this current IT tilde lags from Et tilde by angle phi, and this is my d axis, and angle between q and d axis is 90 degree, right. Therefore, if you take the projection of this one, this is your what you call this XQIT, and this is my angle phi, and this angle will be also phi from the simple geometry. Therefore, this portion will be your what you call XQIT sin phi, because this is phi, this is 90 degree, this is your 90 degree minus phi. So, this portion will be XQIT sin phi, and this portion will be XQIT cos phi, I mean from here to here, right. Now, and this is my RAIT, this is phi. So, this is also your, this angle is also phi, therefore, from here to here this is your RAIT cos phi, right. And similarly, your this portion, I mean from it is marked here, I mean this portion, I mean from here to here, this is my RAIT sin phi, it is written here RAIT sin phi, right. That means, from here to here it is XQIT cos phi minus RAIT sin phi, I mean from here to here it is XQIT cos phi minus RAIT sin phi. Similarly, from here to here it is XQIT sin phi plus RAIT cos phi. Therefore, tan delta I will be simply is equal to you take this vertical one XQIT cos phi minus RAIT sin phi divided by ET plus RAIT cos phi plus XQIT sin phi, right. That is what has been, just hold on, that is what has been written here, right. That is tan delta I will be XQIT cos phi minus RAIT sin phi divided by ET plus RAIT cos phi plus XQIT sin phi, that will be delta is equal to tan inverse XQIT cos phi minus RAIT sin phi divided by ET plus RAIT cos phi plus XQIT sin phi, right. So, this is that simply steady state phasor diagram, that is how to compute actually delta I. Now with delta I known, the dq component of stator voltage and current are given by this. We have seen earlier that ED is equal to ET sin delta I if delta I is known, and EQ is equal to ET cos delta I, right. Similarly, earlier we have seen that ID is equal to IT sin delta I plus phi and IQ is equal to IT cos delta I plus phi. No equation numbers given here, because all these things we have seen in previous lecture, right. Therefore, the remaining machine quantities are computed as follows. Therefore, already we have done this. Therefore, psi d will be EQ plus RAIQ, psi q will be minus ED minus RAID, and this IFD expression also given before. So, IFD will be EQ plus RAIQ plus XDID upon XAD, right. Therefore, and EFD, that is the field voltage, it is equal to RFD into IFD. Equation numbers not given here, because all these things are given before. Now, psi FD will be now is equal to LAD plus LFD IFD minus LAD ID. Similarly, psi 1 D, we are assuming that your one armature winding on D axis will be LAD into IFD minus ID. Similarly, psi 1 Q will be is equal to psi 2 Q is equal to minus LAQ IQ, right, and torque TE is equal to PT plus RA IT square. This all these equations whatever is written here, that has been given developed and given in the previous lectures, right. So, with this we will take one small example. Now, this is example 2. The following are the parameters in per unit on machine rating of a 555 MVA 24 kV 0.9 power factor 60 Hz 3600 RPM turbine generator. It is all these parameters are given in per unit. So, every place I did not write PU like this, right. It is understandable that it is in per unit. LAD is given 1.66, LL is given 0.15, RA 0.003, all are in per unit. LAQ is 1.61, RFD 0.0006, L1D 0.1713, R1D 0.0284, L1Q 0.7252, R1Q 0.00619, L2Q is given 0.125, R2Q 0.02368, right. LFD is assumed to be equal to LAD, right. So, I mean LFD is equal to your LAD. So, here LAD is given. So, your this is assumed that LFD is equal to LAD, right. Now, part A, when the generator is delivering rated MVA at 0.9 power factor lagging and rated terminal voltage, compute the following. 1. Internal angle delta I in electrical degrees, that you have to determine. Then 2. Per unit values of ED EQ, ID IQ, I1D I1Q, I2Q, IFD, EFD, psi FD, psi 1D, psi 1Q and psi 2Q. Part 3, that air gap torque T in per unit Newton meter, right. Assume that the effect of magnetic saturation at the given operating condition is to reduce your LAD and LAQ to 83.5% of the values given above. That we will see when we will solve this problem. And part B, compute the internal angle delta I and field current IFD for the above operating condition using the approximate equivalent circuit of figure 17, right. So, this figure 17 already given before. Now, solution. With the given operating condition, the per unit values of terminal quantities are, it is P is equal to actually 0.90 per unit, Q is equal to 0.436 per unit, ET is equal to 1.0 per unit, although not written many places, but understandable they are in per unit values. IT is equal to 1.0 per unit and phi will be 25.85 degrees, because power factor is given 0.9 lagging, right. So, the saturated values of the inductances are LAD, it is actually given here in the problem, that is your 83.5% of the values given above. So, it is LAD will be 0.835 into 1.66, that is your 1.386 per unit. LAQ is equal to 0.835 into 1.61, it is 1.344 per unit, right. LD is equal to LAD plus LL, that is 1.386 plus 0.25, because LL is given 0.15. So, it comes about 1.536 per unit, right. Similarly, LQ is equal to LAQ plus LL. So, it is 1.344, because here it is 1.344 we have computed, plus 0.15. So, it is LQ 1.494 per unit. Now, first one is internal angle delta I for this. So, we know delta is equal to tan inverse XQ IT cos phi minus RA IT sin phi divided by ET plus RA IT cos phi plus XQ IT sin phi, right. Now, therefore, delta is equal to tan inverse XQ is given 1.494, IT is 1 per unit and cos phi is 0.9, it is given. Now, minus RA is given 0.003, IT is 1 and sin cos phi is 0.9. So, sin phi will be 0.436, right, divided by ET. ET is 1 plus RA IT, RA is 0.003 into 1, IT is 1 into cos phi, that is 0.9, plus 1 XQ is 1.494 into 1.0 into sin phi 0.436. If you solve it, delta will be 39.1 electrical degrees, right, that is the internal angle of the machine. So, only thing is that just you have to compute in correct fashion. Now, part 2, ED, we know ED is equal to ET sin delta I. So, ET is 1 and sin 39.1 degree, that is 0.631 pu, that is your ED. EQ we know that ET cos delta I. So, 1.0 cos 39.1 degree, so 0.776 per unit, that is my EQ. And ID is equal to, we know IT sin delta I plus phi. So, IT is 1 per unit, delta is 39.1 degree and phi is equal to 25.84 degree. So, if you compute, ID is 0.906 per unit, right. Similarly, IQ is equal to IT cos delta I plus phi, that is 1, because IT is 1, cos 39.1 plus 25.84, they are degrees. So, IQ will be 0.423 per unit, right. We also know the field current, this formula or equation we have derived before. So, IFD will be EQ plus RAIQ minus XDID upon XAD. EQ is we have got 0.776, right. So, it is 0.776 and ED is 0.631, right. So, EQ is 0.776, RA is 0.003, IQ we have computed 0.423 minus XD is given 1.536 into ID, that is 0.906 divided by XAD we have computed 1.3x. Actually, in per unit LAD will be equal to XAD. I told you in per unit values your inductance and your reactance all are same. So, in per unit value LAD is equal to XAD, right. So, sorry. So, that is why it is 1 point divided by 1.386. If you compute, you will get IFD is equal to 1.565 per unit, right. So, and we know EFD is equal to RFD into IFD. So, RFD is 0.0006 into 1.565. So, EFD will be 0.000939 per unit, right. So, we also know that psi FD is equal to LAD plus LFD into IFD minus LAD into ID, right. So, psi FD is equal to LAD 1.386 plus LFD 0.165 into IFD we have computed 1.56 as minus, I told you LAD and XAD same, right. So, LAD is given 1.386 into ID 0.907. So, this comes psi FD 1.17 per unit, right. We also know psi 1D is equal to LAD IFD minus ID. So, psi 1D will be 1.386 into in bracket IFD is 1.565 minus ID 0.909. So, psi 1D will become 0.913 per unit, right, and psi 1 q is equal to psi 2 q is equal to minus LAQ IQ. So, that means psi 1 q is equal to psi 2 q, LAQ is equal to minus LAQ is equal to 1.344, IQ is equal to 0.423. So, it is actually minus 0.569 per unit, right. Now, under steady state your I 1 D is equal to I 1 q is equal I 2 q will be 0, right. So, because there only one armature winding is there on the D axis and two are on the q axis, and on when it reach steady state, because they are closed winding, when it is steady state all these currents are equal to 0, right. Now, number 3, the air gap torque, we know T is equal to P T plus I T square R A. So, P T is 0.9 and I T is 1, so 1 square and R A is 0.003. So, basically it is coming T is equal to 0.903 per unit. If you neglect this loss, then T approximately equal to P T, because these are they are very close, right. Now, next is the torque base, the T base. Torque base is MVA base into 10 to the power 6 divided by omega mechanical base, right. So, it is MVA base is 555 MVA into 10 to the power 6, we are actually converting into volt ampere, right, divided by omega mechanical base 2 pi f, f is 60 hertz, right. So, if you compute torque base, that is 1.472 into 10 to the power 6 Newton meter, this is the base value. Therefore, T E is equal to its 0.903 we have got per unit value 0.903, and T is equal to, you multiply by this base value T base, you will get 1.329 into 10 to the power 6 Newton meter, right. And part B, using the saturated value of XAD, we know that earlier we have seen EQ is equal to J XAD IFD, but we are just thinking about the magnitude. Therefore, EQ is equal to XAD into IFD, that is 1.386 IFD, right, and XS will be XAD plus XL. So, XAD is 1.386 plus 0.15, that is XS is equal to 1.536 per unit, we call it as a synchronous reactance, right. From the equivalent circuit, just go back to figure 17 once, this figure 17 with ET tilde as reference phasor, the simple single line circuit, if you see EQ tilde is equal to ET tilde plus J XS into IT tilde, right. So, I am not going to figure 17, just have a look, right. So, there everything is given. So, EQ tilde ET tilde is 1 angle 0, so it is 1.0 plus J XS we got 1.536 and IT tilde it is 1 per unit. So, basically it is your what you call that power factor is 0.5 lagging. So, basically it is 1 angle your minus 25.84 degree, it is lagging, right. So, basically it will become 0.9 minus J 0.436. So, if you compute EQ tilde will become 2.17 angle 39.6 degree, and if you go back to this figure 17, it is given EQ tilde, right, that is your angle delta I. So, this delta I, this is the magnitude of EQ values, and delta is 39.6 degree, right, that is the answer. So, therefore, IFD magnitude, that IFD EQ upon XAD. So, EQ we got 2.17 and XAD we have computed 1.386. So, it gives actually 1.566 per unit, right, that is the current. So, now with this example whatever little bit steady state analysis we have done, that will your what you call, that will clear our your what you call doubts, right. So, these are a simple example and simple phasor diagram, just this kind of phasor diagrams we have already done in power system as well as in machine analysis. So, it is very simple. Next we will move to your just hold on, Next we will move to your swing equation, right. So, because now slowly and slowly we will enter into the dynamics of the synchronous machine. You are aware of this your what you call this swing equation. So, here also we will see the same thing, but step by step, because we have to develop your synchronous machine model in a complete, I mean as far as it is possible as a classroom exercise, that kind of model. Slowly and slowly we have to step by step we will develop this. So, we will start from swing equation, because that is your what you call that most important for synchronous machine. So, swing equation. So, already you have studied in power system the single machine infinite bus, the transient stability analysis, there you have studied. In machine dynamics also little bit you have studied. So, let us see how actually things are. So, when there is an unbalance between the torques acting on the rotor, the net torque causing acceleration or deceleration, that you know accelerating torque is equal to Tm minus Te, right. So, this equation you should not see this number, no need, only you will follow this one, right. So, this is not need, this is for my own clarification. So, this equation is 175, that is Ta is equal to Tm minus T, where Ta is equal to accelerating torque, that is in Newton meter, and Tm is mechanical torque, that is also in Newton meter, right. And T is equal to electromagnetic torque, that is also in Newton meter, right. In the above equation, Tm and T are positive for a generator and negative for a motor. I mean in the Tm and T, they are positive for a generator and negative for a motor. That means this just hold on, this equation that Ta equal T, I mean they will be positive for generator, and if it become negative then it will become T minus Tm for motor, right. So, now the combined inertia of the generator and prime mover means in power plant it is a turbine, right. So, combined inertia of the generator and prime mover is accelerated by the unbalance in the applied torques. Hence, the equation of motion is given by J d omega m dt is equal to accelerating torque Ta is equal to Tm minus Te. This is equation 76, right. So, this one you should not read, this is equation 176, right. Now, where J is equal to combined moment of inertia of generator and turbine, that is in kg meter square, right, and omega m, that is the angular velocity of the rotor in mechanical radian per second, and T is equal to time in second, right. So, this equation you are familiar with this equation from your power system studies as well as machine stability studies. So, the above equation can be normalized in terms of per unit inertia constant H. That H also you have studied, the inertia constant and his unit is second, you are aware of it. So, define as the kinetic energy in watt second, right, watts, because that joule per second is equal to watt, energy unit of energy is joule. So, joule is equal to watt second, because joule per second is equal to watt. So, energy in watt second at rated speed divided by the volt ampere base. Using omega 0 m to denote rated angular velocity in mechanical radians per second, the inertia constant is given by H is equal to your half into j omega 0 m square divided by volt ampere base, right. This equation, this is equation 177, this you should not read. So, H is equal to half j omega 0 m square upon volt ampere base, because half j omega 0 m square is that your what you call, that you are aware of this, the kinetic energy, right. So, that is why, and divided by the volt ampere base. So, H is given like this, right, or just hold on, or J is equal to 2H from this equation only 2H upon omega 0 m square into volt ampere base. So, this is equation 177a, right. So, H is defined as a kinetic energy in watt second at rated speed divided by the volt ampere base. So, half j omega 0 m square is that kinetic energy and divided by volt ampere base. So, that means J is equal to 2 h upon omega 0 m square into V a base. From this equation only, this is equation 177a, right. So, from equation 176 and 177a we get, that means this J value you substitute here, J value you substitute here, use in 176 you substitute here. So, if you do so, you will get 2 h upon omega 0 m square volt ampere base into d omega m by dt is equal to T m minus T e, right. Or you can write 2 h your 2 h d dt omega m upon omega 0 m, right, that this thing is equal to T m minus T upon V a base divided by omega 0 m. What we are doing actually, this 2 h this there, then d dt 1 omega 0 m square is there. So, what we are doing, we are dividing 1 by omega 0 m and another omega 0 m, because omega 0 m into omega 0 m, this part we are writing T m minus T T, right, and this is V a base, this V a base we are being divided by omega 0 m, right. So, this is just to represent this your what you call this mathematical equation, just to make it in per unit values, everything will be in per unit values, right. So, thank you very much, we will be back again.